For those who are requesting for the notes, you can take a screenshot or you can pause and write the question somewhere. Then remember to subscribe kindly. So this uniform circular motion applies under merry-go-round turntables negotiating a curved corner under high speed. That is the key point, under high speed or at a certain speed. That applies more than in racing cars. Whirling a stone on a string, then orbitation or orbiting of the planets. So they all move in a circular motion covering a uncertain angle. So this is the angle we are calling the angular displacement. Then covering a circular distance that we are calling it angular distance s. That is the part of the circumference of that circular motion. So this theta is normally measured in radians. So remember, 1 radian is the angle subtended from the center of the circle, which intercepts an arc equal to the radius of the circle. Therefore, 1 radian is implied when this radius is the same as this circumference here. So to know the total radians for the full circle, we say that the angular distance, which is normally given by the circumference for a full circle, is given as 2 pi r, then divided by radius, which is radius. So that leaves us with the 2 pi. But also, angle at a point add up to 360. So we now say that 360 degrees equals 2 pi radian. So 1 radian will now be given as 360 over 2 times pi is normally 22 over 7. So this will give you 57 point something, which you can now be able to convert the other degrees into radians or other radians into degrees. Then angular velocity as another definition is the rate of change in angular displacement. So remember, angular displacement angular velocity is abbreviated as omega. So therefore, omega is given by angular displacement over time, which is the SI unit as radians per second, because the angular displacement has been said here that it is measured in radians, then time is normally in seconds. So we now say that that angular displacement is the same as the circumference over radius from what we have already seen, the circumference of a radius. So dividing through by t leaves us with this one. The rate of change in angular displacement is equals to circumference over r times t. But distance over time, this s over t, the same as distance over time, implies velocity. Substituting here with the velocity leaves us with omega is equals to velocity over the radius. So therefore, making v to be the subject implies that omega is equals to v over r, which implies that linear velocity is equals to the angular velocity times the radius of the circular motion. We also come here and say that time to complete one oscillation is implied by period. So period is given by the total circumference over the linear velocity. So circumference is 2 pi r, linear velocity is v. But remember, linear velocity here we have said is given as omega r. So therefore, omega r, therefore period can be written as the 2 pi r, which is the circumference over omega r. R goes with the r and leaves you the t is equals to 2 pi over omega, which is the angular velocity. Frequency is normally 1 over period. So therefore, it implies 1 over this period. So that means that the angular velocity, which is omega, is the same as 2 pi f when you make here omega to be the subject. So kindly note this to one point. This is the major point we have found. This is the second major point. This is the third major point. If you have not subscribed, subscribe as we proceed. Then centripetal acceleration is the rate of change in angular velocity. Remember, it's centripetal acceleration. So we said that by Newton's law, remember it is Newton's first law, that a body remains in its state of motion unless acted by an external force. Therefore, this object could have gone in this direction, or this direction, but it's maintained in circular motion because of the centripetal force. Therefore, a body in circular motion is said to be accelerating because of the change in direction of motion and the position of the gravity as it moves up and down. That is for vertical velocity also. Vertical circular motion. Then there is also a change in angular velocity with the time, hence implying acceleration. So we say that if we take this path to be straight to represent the issue of the distance, we say that a very close chord to the circumference, it implies that AB over PQ, remember PQ, this the chord that we have assumed. So AB, which is the circumference over PQ, implies OA over OP. That is the radius over velocity. So that means that this distance that was originally angular displacement over this velocity is the same as the radius over velocity. So making the change in velocity to be subject to get that change in velocity is the same as change in angular displacement times velocity over r. But remember, distance is given by speed times time. So replacing where there is this one with speed times time, it gives us that speed times time times speed is equals to, over radius is equals to change in velocity. Velocity times velocity gives you velocity squared. So then dividing through by change in time gives us velocity, change in velocity over change in time as velocity squared over r, because this will cancel. Then velocity over r, or change in velocity with change in time, implies acceleration. Therefore, acceleration is given as v squared over r. Remember, v squared over r, but we had already said here that v is the same as omega times radius. So therefore, you can also say that acceleration is also given by this one squared, that is omega r squared over r, which leaves you with omega squared r. Remember, force is equals to mass times acceleration. So therefore, the centripetal force maintaining the object in circular motion is now given as either mass times the angular velocity squared times the radius of the circular motion, or mass times linear velocity squared over the radius of the circular motion. So you have these major factors that affects the rate or the force of the centripetal maintaining the object in circular motion. The first is the mass of the object. If the mass is heavier, then you need to know that the centripetal force to maintain it will also be more. The angular velocity, an increase in angular velocity also increases the centripetal force. And if it's not sufficient, remember, the string will snap. Then the radius of the part also affects the centripetal force. Then the application of this topic is more in whirling of a string on an object on a string, the issue of negotiating of a car on a sharp corner, we have said in racing cars, as well as the issue of speed governors. We want to see how the speed governors operates and also how you can adjust them to suit your preferences. Remember, subscribe as we move forward. We have here our first example of calculation. You can pause and write it somewhere, then attempt. A wheel rotates at 45 revolutions per second. What is the angular velocity? Revolutions per second implies frequency. So if you have frequency from this omega is equals to pi f, it implies that the angular velocity, which is omega, will be given as 2 times 22 over 7 times frequency as revolutions per second. Remember, it must be per second because it's 1 over t in SI units. So therefore, if there are revolutions in any other measurement that is not 1 second, we'll have to convert to obtain the time for one oscillation. Our second example is to find the maximum speed with which a car of mass 100 kilogram can take a corner of radius 20 meters if the coefficient of friction between the rod and the tire is 0.5. Remember, a car is normally 1000 and above, but we can just assume, as we have been given here, to be 100 kilogram. So therefore, the centripetal force maintaining the object is given by the coefficient of friction times mass times gravity. Coefficient of friction is 0.5, mass is 100, gravity is 10 to get 500 Newton. Then 500 Newton will now be given by, the centripetal force is given by mass times velocity squared over r. That means linear velocity being made as the subject will be the square root of this one, getting it to be 10 meters per second. So this question actually carries all the areas of the topic. So you can also pause and write it somewhere, or you can even snap it, then attempt it as we move forward. So the first part, a string of negligible mass has a stone of mass 45 grams tied at the end. If the string is 0.6 meters long and the stone is whirled vertically at 6 radians per minute. So calculate part 1, the frequency, part 2, the angular acceleration, part 3, the linear velocity. Then part B, we have sketch the path of the circular motion of the stone. On it, show the position of maximum, minimum, and medium tension on the string when raised at a height of 5 meters. From there, we'll also see how to calculate the maximum tension in the string, the velocity with which the string snaps if exceeded, then they are also implying that it is implying the maximum velocity. We also have to sketch the path followed by the stone after the string has snapped, then then to calculate the velocity at which the stone strikes the ground after snapping, obvious. Then the last part is to calculate the horizontal distance between the point of the stone that's striking the ground and the whirling point. Remember, we can say from the Newton's laws of motion that it is the range or the distance between the 2 points on the ground. So starting with the first part, calculate the frequency. So frequency, we have been given that it is 6 radians per minute. That means it is angular velocity, but the units are not in the SI unit. So you convert from radians per minute to radians per second. So that you move on. Convert 1 minute to second. Remember, 1 minute is normally 60. So that when we come here, we say that the angular velocity, which is 2 pi f, will be given by the frequency. Now, the one that we want, frequency, is normally f over 2 pi. I mean, angular velocity over 2 pi, after making this one to be the subject. So therefore, the angular velocity in SI unit becomes 6 radians per 60, because 1 minute equals 60 seconds. That gives you 0.1 radians per second. So frequency now becomes, you replace 0.1 over 2 times 22 over 7, which gives you 0.0159 Hertz. Or you can write revolution per second if you feel like. The second part is the angular acceleration. Angular acceleration is like A in abbreviations. We say that A is given by omega squared r. That means our omega is here is 0.1. So 0.1 squared times the radius of the pads. So the string is of length 0.6 meters, which becomes 0.6, giving you 0.006 meters per square second. You can also decide and use the issue of A is equals to V squared over R if you feel like, then the same answer will come through. Then the second question is the linear velocity. So we want to see how do you calculate the linear velocity. Linear velocity comes from this one, that V is equals to omega R. So therefore, our omega is 0.1, the radius is 0.6. So V is equals to 0.1 times 0.6. That leaves you with 0.06 meters per second because it is linear velocity. Then here we now have our second part. So sketch the path of a circle of circular motion of the stone. On it, show the position for maximum, minimum, and medium tension in the string when raised to a height of 5 meters. So this one being our object, we can say that it's moving in this circular manner. So it becomes the path. So the minimum tension in the string is at this position, the top position, and it's also at this position that it's able to fall down. Then at this position, B is the average, which is the same as also when whirling in horizontal motion, this motion. Then at point C, which is the lower part, is the one that has the maximum tension in the string, and also the point where the string is likely to break. So the height has been given as from 5 meters from the ground. So you can just have this one as our sketch. Then you also have calculate the maximum tension in the string. So you want to see how do you calculate the maximum tension. So for maximum tension, remember I have said if this one is our circular motion, the maximum tension is experienced down here. So at this position, the tension is given by tension will be the mv squared over r plus the weight of the object. That is the centripetal force plus the weight of the object because it's being pulled downwards, because it has the maximum kinetic energy. So we come and see that tension is given by the centripetal force plus the weight of the object, which is mv squared over r plus mg. So we substitute these values. The weight of the object was 45 grams. So we convert to SI unit, then times the v squared, then over r, plus the weight of the object. That is 45 over 1000 times the gravity, which is mg. That gives you a tension of 0.45027 Newton. Then sketch the path followed by the stone. You have here velocity with which the string snaps if exceeded. So we have velocity as the maximum velocity. Remember, maximum velocity will be at this lower position here. So at this lower position, maximum velocity of the snapping velocity is given by V is equals to the square root of 5rg. If you don't know how this 5rg is coming about, just go back to the videos and you will find one of the videos showing us how this formula is coming about. So it becomes 5 times the radius is 0.6, gravity is 10, to give you this one as the maximum velocity, beyond which, when exceeded, the string will break. Then we have here sketch the paths followed by the stone after the string has snapped or broken. So we now sketch that from this circular motion, it will move from this point, forming a tangent. Then from there, it now flows downwards. So you must show that it's forming a tangent. From this height, it falls somewhere here. Then Roman 4 calculate the velocity with which the stone strikes the ground. So after it has broken here, it will form a tangent as we have seen. Then from there, fall here. So what is the falling velocity at this position here? So you come and say that the velocity at which the stone strikes the ground is given by time taken to reach the ground must be first found. So from here for free fall, we say that h is equals to a half gt squared, because the initial velocity is 0. From s is equals to ut plus a half gt squared. So when this u is 0, it implies, when this u is 0, it implies that the formula remains to be a half gt squared. So therefore, t will be given as the square root of a half times gt squared. So when you form it to the subject, t becomes 1 second. So if t is 1 second, we now come and say that from v is equals to u plus gt, or at, u is 0 from what you have seen here. Therefore, v is given as 0 plus 10 times 1. That means that v is 10 meters per second. So the striking velocity is 10 meters per second. Then the last question, calculate the horizontal distance between the point the stone strikes the ground and the whirling point. So you can say that if this was the height, 5 meters, so the stone moved and fell at this position. So this one is given as the range. So the range is normally given by r is equals to ut. That is the initial velocity times time. This initial velocity is the velocity that it broke with. So we found that the broking velocity was 5.477. So it now say that it is ut 5.477 times time, which is 1 second, to get 5.77 meters. So we shall be solving such and more questions under the uniform circular motion. If you have some that you have an interest to be solved, send it to our email and it will be solved immediately. Kindly subscribe and have a nice time. Thank you.